Russell Impagliazzo, who's a professor at UCSD and needs no introduction. And the talk title is Connections Between Pseudo-randomness and Machine Learning.
Thank you. I'm hoping, so the previous talk mentioned zero knowledge, and I'm hoping to live up to that standard of conveying no knowledge beyond the statement that I want to convey is that really we should always be thinking about connections between different areas, and in particular, the two areas, pseudo-randomness and machine learning, even though they're usually have like disjoint communities, they're really flip sides of the same intellectual endeavor, and we should be like approaching them together. Even if you're not trying to do one or the other, you're going, even if you're doing one and you're trying not to do the other, you're going to accidentally do the other. So they're really the same. So I was trying to do pseudo-randomness. Okay, and I kind of explain why I realized I was doing machine learning when that was not my intention. Okay, so these two areas are like thought of as having like very different motivations. Pseudo-randomness comes from cryptography, from de-randomization of algorithms. Machine learning comes from more applied areas where you're trying to actually understand data, the world, and so on. Why are these kind of intellectually the same? So let me just prove that in a picture, in a series of pictures, I hope. And then I'll spend the rest of my talk giving some anecdotes that are fun for me. Okay, so what is pseudo-randomness about? Pseudo-randomness is about data that maybe has subtle patterns, but where those patterns are not observable to an outsider. They're hard to discover. Okay? Machine learning is about discovering the patterns, the subtle patterns in data. Okay? So, yeah, that is okay. I don't know if the red lines are visible. If you like trace the red lines, you see that this was actually a fish array. Okay. So this means, well, so I just convinced you that they're diametrically opposed, right? That that machine learning's goals are exactly the opposite goals of pseudo-randomness. That's true, but that's why we need to study them together, because you can't study one thing without studying its opposite. Okay, so this is why machine learning and pseudo-randomness are kind of they're directly opposed to each other in some way, which means that their study, we as like intellectual observers supposed to be objective to understand the issues in one are going to be the issues for the other. It's the same kind of background issues about when you can transform one thing to another thing. And of course, we're not actually just objective bystanders. We're actually, like, when we're proving a theorem, we're really rooting for our side, right? We want our machine learning algorithms to work. We want our data to be pseudo-random. And we want it to be not the patterns to be hidden from these machine learners. Okay, so what happens when to get a connection between machine learning and pseudo-randomness? Often there's a psychological barrier. You have to start rooting for the other team. So once you start rooting for the other team, you find that you're doing the other one. Okay, so let me give an example of where, so I'm just going to go through and see where this kind of connection through opposition came up in my own work without my realizing it for the most part. So I'm just going to trace through the many times that machine learning and pseudorandom generators, pseudorandomness in some form, met in my work. And I'm sure there are lots of other people who could give complete disjoint sets where it came up in their own work. But then I'm especially going to say how the Simons Institute enabled a lot of these kind of connections to be made. Okay, but actually, when I started thinking about it, I was going to like say, oh, let's highlight the connections made at the Simons Institute. But a lot of those connections went back many, many years, and I realized that like one of the first connections dates back to 1990, kind of one of these oppositional connections. So what was happening around 1990, especially from my perspective as a graduate student and then a recent alumnus from UC Berkeley, a lot of the excitement was about realizing that the foundations of cryptography, that we could have a very unified foundation for cryptography. Okay. Namely, if one-way functions existed, there were lots of things that we could do with them. Okay, a lot of cryptography was possible based just on a one-way function. And that included pseudorandom generators, pseudorandom function generators, secure signatures, secure bit commitment, zero knowledge, and a lot of other desirable things would come from just having a one-way function. Okay, so it seemed like having a one-way function would be great. But what if we didn't have them? Uh-oh. What if these things don't exist? So is there any like bright side to one-way functions don't existing? Are there any algorithmic consequences for one-way functions not existing? And I guess kind of like my motivation for wanting some algorithmic consequences is I still wanted to believe that one-way functions existed. So if there would be algorithmic consequences that would be too good to be true, that's actually a reason to believe one-way functions actually exist. There would be unbelievable algorithmic consequences. So a result along these lines actually was in a joint paper myself and Leonid Levin in 1990. It actually was kind of tagged on by Leonid to a paper on a completely different subject. So I'm not even going to name the paper. So he came up with a great result that if there are no one-way functions, then you can do average case learning in a very strong way. Okay. The only problem, and he was going to make me an author on this result, so I was very excited. But the only problem is that Leonid either doesn't believe that machines can learn, or maybe he believes that machines could learn, but we shouldn't encourage it. I'm not sure. But he totally refused to use the words machine learning in the paper anywhere. So we had to write a paper, or I had to kind of like translate what Leonid had already written, because you know how Leonid writes papers. It's like the 3-page paper that is like 3 PhD theses to interpret. Okay, so and takes like a decade. So I had to like hint at what the significance of his result was without saying it. And I think I totally failed. So I think no one actually, even people in the area, don't know about this result. Fortunately, they do know about related work by Avram Blum, Merrick First, Mike Kearns, and Dick Lipton just a little later that really kind of explains the connections between one-way functions and machine learning a lot better in a lot more accessible terms by, for example, using the term machine learning. Okay, so okay, so and this actually you can, this is I say like, not a lot of people know this result. To tell the truth, I don't really know this result in the following sense that, again, when I'm trying to, I've like taught this in different classes over the years, and every time I teach it, I not only give a different proof, but I give a different statement of what the result is, because I want to like explain what kind of learning is possible. And you can, you can like say, oh yeah, pack learning is possible on distributions that are sampleable. That's true, but it doesn't really explain the complete significance of the result. It's a lot stronger than that. And actually, very recent work by Moni Naor and Yogev showed even further generalization. Again, in a paper that doesn't mention one-way functions or machine learning in its title. It's actually called something like something about Bloom filters. And so you really wouldn't know to look for it in that paper. So, but it's actually a pretty nice result that even extends our work and shows this very strong learning is possible if there are no one-way functions. Okay, so here we have the opposition. If one-way functions exist, pseudorandom generators exist, very strong pseudorandom generators. If one-way functions don't exist, machine learning. And the techniques that we use to get those two results are pretty much identical. Okay. So, so I ran into this kind of connection a few years later when I was trying to like avoid doing the same kinds of presentations that I always did. So I was trying to like move out of my comfort zone because I had been teaching this grad topics course, and I always picked topics that I was very comfortable with based on my own work or people that I already knew about. And I said, that's not the way to teach a topics course. You shouldn't teach things you already know about. You should learn new things and teach them. So I said, I'm going to learn something completely different, something I know nothing about, and I'm going to try to teach that and stretch myself. And so my friends at CMU were really excited about Jeff Jackson's PhD thesis in machine learning, pack learning of DNFs. I said, well, I'm going to learn this paper and present it to my class, really stretch myself, learn a completely different area that I know nothing about. And then I started reading the paper, and it had three main, I'm not trying to, so it's a really good paper, but it had three main techniques that he used. The first one was Fourier analysis. I said, okay, well, I guess I don't have to start from, I had just presented Fourier analysis in the class, Lineal Mensur and Nassan. Okay, well, that'll be familiar to my students. Good. At least we have some, it won't be a complete leap for them. Okay, then how about the second chapter? The second chapter was about an algorithm by Kushilevitz and Mensur for finding large Fourier coefficients. And when I thought about it, this was this Goldreich-Levin theorem from cryptography. Okay, and I'd already taught it. Okay, so, there must be something in this paper, in this thesis, that I haven't already taught in the class, and there was. The last chapter was about boosting. The last ingredient was boosting. And I hadn't taught it before. I had just used it in my most recent paper on pseudo-randomness without knowing what I was doing. So the paper was called the hardcore distribution lemma, and it turned out that what I was doing in that paper was boosting. So I'm going to make a digression and actually tell you what the hardcore distribution lemma is and what boosting is and why they're the same. So what I was trying to do is go from a somewhat hard problem to a really hard problem. And a lot of times the intuitive reason why, say you have a problem that no algorithm can get the answer right more than 95% of the time. And it's a Boolean problem. Yes, no. So we always started by saying, well, intuitively, what should be the case is that 10% of the time, the problem looks like a coin flip, and 90% of the time it's easy. And that's why you can't do better than 95% of the time. Of course, you can't, that's the intuition, but you have to do the argument, you have to do something completely different as far as the formal argument. And then I thought, maybe you don't. Maybe that's what's really going on all the time. And so I came up with this hardcore distribution lemma that actually showed that if you're hard 95% of the time, there's this 10%. Actually, I proved 5%, and then later Hohenstein proved 10% part of the space where the function is essentially pseudo-random. Looks like a random bit. Okay. And I had one, there were actually two proofs in this paper. One that I came up with, and then that seemed somewhat constructive. Of course, it's, we're talking about complexity, so how constructive can it be? But it seemed like it went in stages, and you started constructing a circuit. And so it seemed, I liked that aspect. But then Noam Nassan came up with a completely non-constructive proof, just invoking the min-max theorem. So I was really happy when I realized that what I was doing was actually an algorithm, and it was actually a useful type of algorithm, a boosting algorithm. Okay. So okay. So what is a boosting algorithm? Okay. So it actually has there are many uses of the word boosting in machine learning now, but it started as a way of making a pack learner. So pack learner gets black box samples of a function, a Boolean function, and is trying to output from those samples a function that agrees with the labels, say 99% of the time. And well, a much weaker goal is, let's just get an algorithm that agrees with the sample, outputs a hypothesis that agrees with the labels 51% of the time. Okay. Well, there's a huge gap between 51% and 99%. And what a boosting algorithm does is it converts weak learners to strong learners. It takes the 51% learner and combines different runs of this 51% learner on different weightings of the inputs until it gets a 99% learner, 99% hypothesis. Okay, and this has been a really useful idea, both in the theory of machine learning, but also in applications of machine learning. For example, this is, I think, the people who introduced boosting, Shapire, Freund and Shapire, and maybe Mike Kearns getting the Kushilevitz, not the Kushilevitz, the Kanalakis Prize. Kushilevitz will come up there, but in a minute, but that's not who I'm talking about now. Yeah, that's not who the prize is named after. Okay, so okay, so and by trying to just understand this this idea from complexity theory, I had accidentally rediscovered boosting. And the great thing is that I had discovered it actually was a kind of useful new twist on boosting that I had come up with, called Servideo and then Clivens and Servideo, called smooth boosting. And the reason why this was a useful twist is that in general boosting algorithms, even the most successful ones, they have this kind of arbitrary reweighting of the inputs. And under this reweighting process, sometimes one of the inputs just becomes more important than everything else combined. Okay? And if that one was mislabeled, And that, one reason why it becomes more important is that you keep on getting it wrong. And you keep on getting it wrong because the answer was wrong, that you were given was wrong. So then it just becomes really more important, and the noise has just overwhelmed the rest of the algorithm, rest of the data. Okay. In smooth boosting, we have a control over how much we can reweight data, so that maybe you can double or triple the original probability, but not more than that. Okay. And or if you're going for 99% accuracy, you can multiply it by 100. So for boosting algorithms, it's actually turned out to be useful for preventing overfitting or use in somewhat noisy data. Okay. And for our purposes, this kind of bounded reweighting actually guarantees that the hardcore set we find is 10%, not just a vanishingly small fraction. But if you have any of these smooth boosting algorithms, you can use it to prove a dense hardcore distribution lemma just by, again, what I said, you root for the other team. So in the boosting algorithm, we have this weak learner. We're running it. We're reweighting the data, running the weak learner again, reweighting the data. And what we hope is that this weak learner keeps on succeeding. And so we eventually find a hypothesis that outputs the function 99% of the time. In the proof of the hardcore distribution lemma, we do exactly the same process, except we're hoping for the weak learner to fail. We know that the strong learner will not succeed because there is nothing that computes the function 99% of the time. So we're waiting for that weak learner to fail. And when that weak learner fails, we pounce, and that's our hardcore distribution. So again, it's just changing the success condition so that failure equals success. That makes a difference. So this hardcore distribution lemma turned out to actually be, well, I didn't, later, there was like an even more kind of intricate web between topics in pseudo-randomness and topics in different goals in machine learning, and pseudo-randomness from complexity, pseudo-randomness from a graph theoretic point of view, pseudo-randomness in number theory even. And the person who kind of helped reveal this connection to me was Luca Trevisan in 2007 when I was at the Institute for Advanced Study. So he gave so there'd been like this really recent breakthrough in number theory by Tao, Green, and Siegler that showed that the set of primes had arbitrarily long arithmetic progressions. And at one point in this argument, they start talking about pseudo-randomness of the prime numbers, or a pseudo-random distribution where the prime numbers is big in this pseudo-random distribution. So that kind of like piqued the curiosity of some people like Luca in complexity theory. How is this pseudo-randomness idea being used in pure math or in number theory? Whether mathematicians consider that pure math or not, I don't know. Okay, so he looked at this. He, Reingold, Tulsiani, and Vadan looked at this argument from the number theorists and kind of like codified it and translated it into complexity terms. And I should mention that when they did the translation, it turned out that there was like related work already being done in the complexity by Barak, Sheltiel, and Wigderson. Again, like exactly, here I'm trying to give a historical talk, and like every historical talk in mathematics that I'm aware of, things, when you actually look at the history, there's like the story you want to tell, and then there's the actual history, and in actual history, things happened in the wrong order. The story makes a lot more sense than what actually happened. So, okay. So what is this? What was going on in this? What was the fundamental issue in this mathematics and in this number theory work? And so it's actually like a really kind of important methodology or approach to that applies to lots of different areas in mathematics, computer science, and so on, called the randomness structure kind of trade-off. Okay. So a lot of objects, they have a lot of kind of apparent structure when you look at them at a high level. Okay. But when you look at the details kind of look random. Okay. So you want like to say, to explain the object, you want to say, here's a high level structure, and then just fill in the details at random. It won't be the same, but it'll be a kind of model, mathematical model of what's going on. And there are lots of different contexts that we can apply this to. You can like be looking at geometric distributions, points on the square. You can be looking in the complexity theoretic point of view, where you're looking at the uniform distribution and subsets from the uniform distribution, and you want to like look at models with respect to tests that are efficiently computable. Okay, you can look at what the number theorists did. They were looking at the distributions on the integers, and the class of tests turned out to be the functions of Gower norms. Okay, or it also makes sense in graph theory to look at the tests being cuts and looking at the subsets of vertices in a graph and looking at what fraction of edges get cut. So I guess the distribution is on edges in a graph, and you're looking at tests that are cuts in the graph. Okay. And what the general principle says, and I said there's lots of like different variants from the different communities that came up with this idea, saying like you've got some subset of your universe and you want a good model for it, and one of two things happens. Okay, either you find if your set, we'll think of it as a small set, sparse set. Okay, either you find a really narrow region definable by your tests that contain a lot of your sparse set, and so you show that the set is small, or you find this very big model somewhere else in the somewhere else in the universe, doesn't have a priori a lot to do with your small set, but as far as the tests are concerned, it looks like your small set. So either your set can be proved to be small, or it looks like it's big. And they use this in the case of the primes to like show that the primes are too small to use some techniques of Zemaretti that show that large sets, dense sets, have large arithmetic progressions, but they look like they're large as far as the tests are concerned that determine arithmetic progressions. Oh, my word. Okay, so I'm not only over the advertised time, but I'm already over the extra time. And this was the they're giving Prasad a time warning that's much too late. Okay, anyway. So the point is that I will try to give Virginia the podium in as little time as I can manage it. The point is that this whole thing turned out to be equivalent to the hardcore distribution lemma, which meant we could get an algorithmic version that was based on boosting. Okay. And when you do it, it turns out to be a lot like the idea from machine learning of generative adversarial networks. Okay. And then in 2017, there were the machine learning and pseudo-randomness workshops, programs at the same time. And so I got to have a lot of interaction trying to like sell this program to some of the machine learning people. And I think it worked out great. So there were other times when I made such a connection. And and one of those times Tony will talk about tomorrow. So while I hope I convince you that pseudo-randomness and machine learning are kind of like evil twins of each other. Which one's the evil one? I won't say. And so that means that we should study them together. And the way to study them together is to bring diverse teams of researchers to the same place, have them communicate, and that's what the Simons Institute does, and that's what I hope it will continue to do for a long time.
One quick question.
Thank you. So aligned with your presentation, you hit very well all the papers. So is there any chance to have the references somewhere?
Well, I will send a complete list of the papers I mentioned in the talk once I write them. Because some of them don't actually exist yet. And they have been in the process of coming into fruition for a number of years, as you can tell.
So I have just like a comment, not a question. So the Shapiri boosting, I mean, I remember from MIT, it was sort of following taking a crypto class on where this whole idea of amplifying hardness was front and center. So it's not surprising. I mean, not
okay,
to the level that you're saying in terms of really matching parameters and constructions, but
yeah,
that's good point.
Okay, so maybe I should just say it was surprising to me, but people who've been thinking about it before maybe would be less surprised. Well, okay, so maybe you could tell me about that.
Okay, thank you, Russell, for the insightful talk.